Okay, so we'll wait for 1 or 2 more minutes. People are still logging on, so we'll wait for a few more minutes and then we'll start.
When
will we get the quiz marks?
Quiz marks, quiz is taking some time to grade. You know, the policy of ours is that the same question is graded for all the students by one tutor. So one single tutor has to grade 603 copies. And so there's a little bit of struggle there. So yeah, they're trying to get it done.
Sir, what will be the format of the midsem?
Yeah, let me come to that. So let's just a minute or two and then we'll start. All right, so let me share the screen. Okay, so the first thing is for today, discussion hour quiz. Unless I say otherwise, every discussion hour is likely to have a small question at the end. So for today is the sinusoidal analysis or phasor analysis of circuits, a simple circuit for which you have to do the analysis. And the other thing is, this is the last week before the midsem. So we won't have a individual tutorial. I'll hold the common tutorial on Friday. And the tutorial quiz will be on the Bode plot. The sketching of the transfer function that was there in the last lecture. So that's, and we'll discuss whatever, if you send me your queries beforehand, your doubts and other things we'll discuss on Friday during the tutorial hour. So that's going to be one single common tutorial hour. And so that is there. And then coming back, all of you know our midsem is on 18th of October. And slot number, last slot is there. So that's a fifth slot here, 6 to 8, right? So it's a 2-hour exam. The exam, again, 2 hours have been allocated to us. It would be an hour and 45 minutes, 15 minutes for winding up, uploading, all of that. The sharp deadline will be 8 o'clock. All right, and the syllabus is still everything that we have covered till the last week. All the lectures that were posted, homework assignments, everything till lecture number 16, I think. That's what was posted. So this week's lectures that I'm going to upload soon will not be there. That's part of midsem. Any other queries?
Sir, can you please release the solutions of homework 4?
Homework?
Homework 4.
Yeah, last homework. We'll release it soon. Yeah. In either today or tomorrow, we should do that. Any other? Any other quick queries?
Hello, sir.
Yes. Yeah, go ahead. Hello, yeah, you have a question? Can you please release upload homework? Yes, homework, upload the homework 4, I'll upload as quickly as possible. I'll do that. Quiz 1 has not been graded as yet fully, so please hold your comments regarding that. It's not done as yet. But once all the grading is over, I'll announce it. In frequency domain filter, I can understand through only sinusoidal, but what for non-sinusoidal frequencies? So the idea was
Earphone का
that
है?
we are characterizing
Earphone पता
the.
है?
Please, everybody, keep it on mute. Everybody, keep your microphone on mute. So the idea is for any other frequency, for example, let's take a speech signal. And let's say your speech signal has some, let's say it's corrupted by noise, and you want to get rid of the noise, and or for example, let's say an equalizer. You want to amplify certain frequencies more and attenuate other frequencies in a relative manner. So anyway, so the signals are non-sinusoidal, but all the analysis, everything is valid, right? So no matter what signal I take, it unlike a sinusoidal signal, it will not be a single frequency, but it will be a band of frequencies. For example, my speech signal may lie somewhere between, let's say, a few tens of hertz, 20 hertz or 30 hertz, up to maybe tens of kilohertz. So it will be a band of frequencies. So any signal that I'm talking about, I can, through Fourier transform, Fourier series, I can transform them into a sum of sinusoids. And thereby I can evaluate what my filter is doing. My filter will tell me which frequencies is attenuating, which frequency is passing, and therefore, we are looking at it one single frequency, but you said there will be 5 major quizzes. Is this now possible since already midsem and 4 quizzes are left? Yes, it's still possible. We'll do it. We'll do it. Don't worry, we'll manage. See, the reason why I don't want to hold too many quizzes also right now is the circuit analysis part is still a sort of a background, I would say. It's still a background, and that's why, although it's necessary, all the techniques, all the tools that we are learning is necessary to understand circuits in general. The more interesting things will happen once we go to semiconductors, analog circuits, digital circuits. So that's where we'll hold a lot more exams. All right, so the design problem, I was waiting if anybody would ask. Nobody sent any email, nobody was eager for the design problem. So I'm hearing somebody asking for it.
Sir, I asked
Yes.
to the tutor, I called him, but he said nothing has been informed to us.
Okay, nobody asked me. I didn't get a single email. I got 300 emails saying I couldn't submit quiz on time, but nobody asked me about the design problem.
So we asked.
And I decided to hold it to I decided to hold it to see how much interest people have, because it's not marks oriented and all that. So I'll post it anyway. I'll not put a deadline. I'll post it. You can try maybe after the midsem. Let's you have various exams coming up, so I'll leave it after the midsem.
Sir, we had written
Good.
it
So
on the forum.
Forum. Okay, I didn't check. Lots of forums are there. I didn't happen to check. Okay. All right. But some of you can directly write to me as well. In between lecture 6, with that little part of semiconductor in various lectures come from, will it happen now? In between section, I don't know. Not really. Okay. So yes. So we will have those design kind of a problems. To more realistic problems, so we'll have that. I'll add it up in subsequent lectures. So in today's lecture, today's discussion, I wanted to show you. You see, in an undergrad course and in an undergrad curriculum, you don't get exposure to some of the latest things that are happening, let's say, in the field of electronics. I mean, you look at most of the courses are foundational courses, and the things that are happening now, they will probably enter your textbooks 20 years from now. it takes time for something that is happening at the cutting edge of research to eventually come as part of an undergrad textbooks. So a lot of excitement that is there sometimes doesn't come through in introductory courses. So I just wanted to, as a senator, you should have mailed. Anyway, I wanted to show you a few interesting things. There are many things that are happening, but a few interesting things that are happening in the field of electronics. As an example, you look at this €5 note, right? Your €5 note that you see here, and this part here, this part that you see here is actually a circuit. It's actually a circuit that has been, so it's paper, the currency note is paper, and the circuit has been printed onto the paper itself. So the transistors, resistors, and capacitors have all been made on the on this currency note. So some of you may have read about, yes, there was a lot of news about that the currency note has a chip. A currency note has some chip. So this does not have any chip embedded in it. See, the problem with an IC is if something is embedded in it, maybe it can be taken out also, or it can be added onto a fake currency note. So when you have something discrete, you can add it and you can take it out also. But in this case, note that the circuit has been made itself on paper. So you cannot really take it off. The transistors have been made on paper, the resistors have been made on paper, the capacitors have been made on paper. So the entire circuit has been made on paper. And so this is being used for anti-counterfeiting to prevent, so it's a complicated circuit, and very few people will have the ability to make circuits on paper. Okay, so this is what we call as banknote electronics or paper-based electronics. So transistors and others are not just confined to silicon and germanium and other semiconductors that we have read of. This is not done in India. Well, in IIT Kanpur also we are making some transistors on paper. We have a National Center for Flexible Electronics, and we are doing some of those things here also. All right, so I just wanted to point out that you can do electronics on, besides your traditional semiconductors, you can do it on paper itself. Okay, so that's an interesting product. Let me show you something else also. So look at this example. This is a Braille display. So all of you are enjoying your e-books and you have Kindle and all of that is there. So what about people who are blind? What about them? So this is a e-book kind of a thing for blind people. So all these things that you see here, these are actuators that are there. You can feel it, and electronically they can move up and down, and you can have different Braille characters here. Right. So this involves again transistors and pressure sensors and all of that made on a flexible piece of rubber. So this is a electronic e-book for Braille e-book for blind people. So that's so again, these are not your traditional rigid ICs, but the whole thing is actually an integrated circuit, but with a flexible form factor and made on rubber kind of a material. Right, so that's a sheet type Braille display. These are the things that you guys might have seen, various kinds of electronic tattoos. Tattoos kind of a thing, or an artificial skin kind of a thing. And the Braille characters are, let's see, what is the question? Braille characters are? No, the Braille characters here are dynamic, yes. So depending on, you would have some, I guess, some controls and it's like a page or a half a page or something, and you can scroll through. So a blind person can scroll through and then feel it, right? So the entire book, just like Kindle and all, the entire book is stored and can be carried. All right, so these are, there are a variety of products that are being developed, which are like electronic tattoos. So these are, again, there are some transistors, of course, here, and there are various kinds of sensors. For example, you could have a UV sensor, which will detect how much exposure to UV light you've been exposed to. And based on that, maybe, it can be coupled to your smartphone and you get a message that there's too much UV exposure or things like that. So these are, again, you can see here, these are circuits made on a very, very thin sheet of plastic. Very thin sheet of plastic, which is then stuck to the skin, and then it provides a useful information. All right, so these are, again, examples of flexible circuits being made on plastic rather than on traditional semiconductor. I wanted to introduce, although we have not done that, I wanted to introduce you to, you may have some idea about how electronic devices are made. For example, after the midsem, we'll start our discussions related to that. So when you're making things on silicon, so you're making basically on a crystalline, the silicon is a crystalline material. So basically you take crystals of silicon, and if you recall your school days, you have to create N-type, P-type, all those different kinds of layers. And we had some discussion on MOSFET. So you have to maybe deposit a silicon dioxide and then on top of metal to create a metal oxide semiconductors and all that. So the processing is done on a crystalline silicon. And to grow an oxide on silicon, you require temperatures of 800 or 1000 degrees. So that's how you grow silicon dioxide on top of silicon. And then you deposit a metal and you etch it. And, it's a complicated series of steps that are there to make it. A very different way of making circuits is, let me show it to you, how a different way of making circuits is being carried out now. Not as a replacement of silicon, but for various other applications. So the idea here is that it's not just silicon and germanium that you have read are semiconductors. It so happens that even polymers can act like semiconductors. So polymers that you may have read in your school 12th class textbook, polymers are mostly, they act as insulators, right? The insulators. Yes? Any question? So polymers are normally insulators, but it would be shocking for you to hear that about, I would say 1970s, maybe you've not heard of it. 1970s, what people discovered was that if you take polymer and you add certain impurities to it, a polymer can become almost as conducting as a metal. Almost as conducting as a metal. So, for example, copper may have let's say, a conductivity of 10 per minus 6 ohm centimeter, or a resistivity of 10 per minus 6 ohm centimeter. You can take a polymer and by a suitable polymer and add some impurities to it, the usual process of doping, and you can make it maybe 10 per minus 5. So not as good as copper and silver, but pretty close to it. And now, so polymers can be insulators, obviously. Polymers can be conductors, as I just told you. Polymers can be conductors. And then people discovered that polymers also have, if you recall, semiconductors have energy gaps. Silicon has 1.12 electron volt, and others have different energy gaps. So polymers also can act like semiconductors. So people discovered that polymers can, for example, emit light. Polymers can absorb light. So polymers can act as semiconductors. So this is very interesting that you have polymers which act like insulators, certain polymers which can act like insulators, some other polymers which can act like conductors, and some other polymers which can act like semiconductors. So to make an entire IC, These are the three different kinds of materials that you need. You need semiconductors and you need insulators. Remember MOSFET, you need an insulator, oxide, it acts like an insulator. And you need conductors, of course. You need wires to connect different devices and all of that that is there. So three different layers you need, conductors, semiconductors, and insulators. You can do that with polymers. Now, the interesting thing about polymer, as you would recall, is that polymers are these giant organic molecules, chain of organic molecules, and you can dissolve them in solvent. If you choose a suitable solvent, the polymer can be like a liquid. So now you can imagine that you have a liquid conductor, you have a liquid insulator, and you have a liquid semiconductor. So now let me illustrate what you can do, right? So imagine that you have an inkjet printer. If you recall your traditional inkjet printers that are there are these three different cartridges that are there. There may be a color cartridge. Within it, there may be red, green, and blue. Let's simplify. Let's say there are three cartridges, red, green, and blue. And the red one will have a red ink in it, and the blue will have blue ink, and the green one will have green ink. So now think about the following. I take my inkjet printer, and instead of red, green, and blue, I fill it up with the red one. I fill it up with an insulating ink, because we just said polymer is a liquid. So an ink, which is a insulating ink, and the green one is a semiconducting ink. And let's say the blue one, blue cartridge, I fill it up with insulating ink or the conducting ink. Okay, so we have three inks: insulating, conducting, and semiconducting. So imagine that. So now what I can do is I can take my inkjet printer and I can take a plastic or a paper substrate or whatever other substrate that I have, and I can print these metal or conducting lines. By the way, it's also very interesting that a metal like silver or gold that you're familiar with, and you know that it melts at very high temperatures. Gold would melt upwards of 1,000 degrees or so. But if you take gold and you make nanoparticles of gold, nanoparticles means if you can create gold particles of nano dimensions, those small gold particles will melt at 100 degrees Celsius. Now, I'll not go into the details. So the same gold, which melts at 1,000 degrees Celsius, if I make nanoparticles of gold, is going to melt at around 100 degrees Celsius. So you can imagine I can take nanoparticles of gold, disperse it in a solvent, and I fill it up in my cartridge and I print nanoparticles of gold here, right? So what will happen is that the solvent will evaporate, leaving behind the nanoparticles of gold. And if I heat up my substrate to about 100 degrees Celsius or so, all those nanoparticles of gold will melt and they will fuse together to form a film of gold over here. Or I can form a film of silver over here. So the point is, I'm trying to tell you is we can print metals onto a substrate. Or I can take a polymer, I can print conducting lines like this here. Right? So let's say we print two conducting lines like this here. Then I use a different ink. Let's say it's a semiconducting ink, and I print on top a semiconductor here. Then I take a different one and I print something else on top of it, a insulator on top of it. Then I print again metal on top of it. So by this process, what I'm trying to tell you is that I'm printing metals or conductors, I'm printing semiconductors, and I'm printing again insulators and metals again. What I can do is I can create something like a MOSFET that I talked about, a field effect transistor. Yeah, Nitin Gupta, go ahead. Nitin, Jaswant, yeah, go ahead, please. Nitin, you have a question?
No, sir.
Okay, Jaswant has a question.
Sir, ask
Okay,
Nitin
so
to
anyway.
mute himself. He has not muted for a long time.
Yeah, please, everybody, mute your microphones. So what I'm trying to tell you is through this that I can take an inkjet printer and fill up the cartridges with insulating, semiconducting, and conducting inks. And thereby I can print these layers one on top of another. And thereby I can create a field effect transistor. Now, you can also know that if I have a semiconducting ink and I create a certain pattern, then I can make a resistor. And to make a capacitor, all I need is a conductor, on top of it an insulator and another conductor. So I can make resistors, I can print resistors, I can print capacitors, and I can print semiconductors, I can print all or transistors, I can do all of those things through an inkjet printer. So let me show you an inkjet printer. So here is an inkjet printer, actual inkjet printer. Of course, it's customized for semiconducting, for these kinds of applications. And there are multiple cartridges in it filled with different kinds of inks that are there. And thereby, if you now basically your circuit is nothing but a file, a file, and you send in this digital information to this inkjet printer, then accordingly, according to the information contained, it will print metals and it will print different inks on top of at different places, and thereby create an entire circuit. So you can take an inkjet printer and you can print an entire circuit on a piece of plastic using polymers or organic compounds which act like semiconductors and insulators. So you can print an entire circuit using this particular approach. Not only that, let me show you something else here. Imagine being able to produce electronic devices in a continuous process similar to the way newspapers are printed on a flexible sheet of plastic 1 meter wide and 10 kilometers long. So this is the way newspapers are printed, right? You have these rollers and you have a paper, and there are different kinds of printers that are there, and it goes from one roller to the next roller, and so this is what we call as roll-to-roll printing. The only difference is now, instead of printing with normal graphic inks, we have now functional inks, semiconducting inks and conducting inks and insulating inks, and thereby we are printing circuits. So we have a roll-to-roll process, and using this roll-to-roll process, you can print circuits like this here, in this particular manner. Of course, you can imagine that the resolution that you will get through this particular kind of a process, resolution is poor. In the sense that, if we go back, even an inkjet printer, the ability of an inkjet printer to print two very close lines is very limited. Maybe I can print two lines which are, let's say, 50 micron apart. Or, if I'm very careful and state of the art, maybe I can do 10 micron or something like that with difficulty. Now, where this length comes into picture is in the speed of the devices. In the speed, if this is a transistor and this is source and this is drain, then it takes, in very simplistic terms, it takes some time for electrons to travel from source to drain here. And the transit time is ultimately related to the frequency, switching frequency of these devices. So the resolution then limits the speed. So these are very interesting ways of making circuits. You can make it on plastic, you can print it on paper, but these are slower circuits. They will not work at gigahertz speeds that we are familiar with. They'll work at much lower speeds. But there are many applications where perhaps you don't require very high speeds. And if, for all applications, you don't require if you have a thermometer, electronic thermometer, and you're measuring your body temperature using a thermistor, you don't require a gigahertz processor there. And slower circuits, if you get your temperature reading in a couple of seconds or half a minute, it won't bother you. So there are applications where you may not require very high speeds, and these things can become. So these are still at research stage. Jitesh, yes? Jitesh has a question. No, okay. So inkjet printers are here. These are roll-to-roll printers that are there here. We have roll-to-roll printers in our campus also for printing semiconductors and conductors and insulators. So we have that also capability in our center here at Flexible Electronics Center. And what are the things that people are trying to do? Okay, so let me just give you one or two examples. Take this RFID, radio frequency identification tag. All of you may be familiar with these RFID and NFC. If not, read a little bit about it. So RFIDs are basically it's a small IC embedded. Normally, it's a IC along with an antenna and embedded, let's say, in a card kind of a thing, plastic card kind of a thing, and then it can interact with the reader. The reader can send an electromagnetic wave, and the RFID responds by sending some information, maybe the passwords or account information and things like that. Right? So this is a standard. For example, one of the standards for RFID is that it operates at a frequency of 13.56 megahertz. And as I said, the RFID, so it sends an identification information. So, for example, RFIDs have been around for a long time, and people would like to put it on practically everything, from a medicine foil to to a Lay's packet of potato chips or whatever. These companies are interested in monitoring the sales of these things, and also supply chains and things like that. So they're interested in putting RFIDs on virtually everything. They're not able to do it because they're costly, because there is a antenna there, and of course there is a silicon IC also there. So the idea is that using the technology that I just described, that if you could print some of those RFIDs, maybe then the cost can come drastically down, and RFIDs can become very, very cheap, and thereby enable a number of products. So in this case, this group of people are trying to use roll-to-roll printing that I just talked about, and they're trying to print an RFID. So you can see a very simple circuit of an RFID. Some of the things that perhaps you can identify, we have a kind of an antenna here, basically inductive coupling, an inductor here, an inductor here, and the two are mutually coupled, let's say. So you have a sinusoidal signal that is coming in here. These are nothing but, you can see some diodes and capacitors that are there. So basically a rectifier, which you'll see soon, rectifiers circuits. And then there is a transistor-based circuit, which is basically, sending some, carries the information about the account or identity of the person there. And so this is what they're trying to do here. You can see here that through it's a roll-to-roll process. So there's a plastic sheet which is fed, and then the antennas are printed, and then there are all these diodes are printed, and capacitors are printed, and it goes through and finally comes out. And look at that, they're talking about printing at a speed of 5 meters per minute. So 5 meters of circuit will be printed per minute. So that is the idea, that very, very high throughput. And even faster people are talking about. So if you can really make these things and they can match the performance of some of the silicon ICs that are there, like 13.56 megahertz RFID is not a very high frequency RFID, okay? 13.56. So here they were able to make a 13.56 megahertz RFID using this roll-to-roll process that you see here. And some of the things that we are studying, LC circuits and all that, are the antennas, for example, are nothing but tank circuits. So this is where your coil is there. Inductance coil that you see here has been printed and onto the plastic substrate, and there are capacitors and there are transistors, all of that here. So this is the completely printed RFID that is there here. Okay, so as an example of, now the thing is, note that I've said that electronics is not something, of course, electronics can be used by, as I've been saying, by everybody to improve any system that any problem that they're thinking of. But to create an electronics like this, you would realize it's not just an electronics engineer or an electrical engineer who's involved in it. When you're talking about roll-to-roll printing line, and we are talking about the printing process, so the whole thing is being developed in close collaboration. Electrical engineers are working with chemists. Chemists have to come up with new kinds of polymers which act like very good semiconductors. One of the properties of semiconductors, important property, is mobility. What is the mobility of electrons and what is the mobility of holes? So electrical engineers are working very closely with chemists to come up with new kinds of semiconductors, new kinds of conductors here. So chemists play a very important role. Chemistry plays a very important role. Mechanical, of course, you can see a very important role in all these printing processes, how to get high resolution printing, all of those. Mechanical comes into picture here. Chemical engineering comes into all the disciplines that are there, it comes into picture here. Fluid mechanics, surface tension, all of that is very important. When you drop a fluid, one drop onto a substrate, what happens to the drop as it lands on the substrate? Does it get smeared? Does it stay in place? All of those things are very, very important. How do you formulate an ink such that it forms a very nice film? So the surface chemistry, surface tensions, all of those things are fluid properties. Those are very, very important. So a lot of these disciplines, they all come together to finally create let's say, an RFID that you see over here. Okay, so sometimes, in fact, as an electronics engineer, when I was doing my undergrad at Kharagpur, I had to do fluid mechanics course and an organic chemistry also. And at that time, of course, I was wondering, as an electronics engineer, what am I doing chemistry again? Or what am I doing with fluid mechanics? Now that I work in this particular field of flexible electronics or organic electronics, I see how relevant they are. How I had to open my, I had to actually borrow my son's 12th class chemistry book and relearn some of that organic chemistry. Anyway, so the point is, many of the things that you're learning, maybe you cannot see at this stage how all those things come together. But believe me that when you look at complex product, complex technology, many of these things have to come together: chemistry, material science, mechanical engineering. All of these things have to come together to create a product. So it's a very interdisciplinary field. The boundaries that we have created between chemical and material science and all of that are artificial boundaries. You would be surprised to know, as I said, we have a National Center for Flexible Electronics. The first coordinator of that particular center was an electrical engineer. Then the next coordinator of the center was a physicist. Then after that was a material scientist. Then the coordinator of that particular center was a chemical engineer. You can imagine a chemical engineer, a coordinator of Center for Flexible Electronics. The present coordinator of that particular center is back to an electrical engineer, right? So all of these fields are related together. They all have, implications for each other. Anyway, so that's the other thing. Look at this particular process. So when you inkjet printing of single crystal films, right? So there's a lot of research going on. So when you take a material in the form of a fluid or a fluid, and you drop it as onto a substrate, and you're trying to form a film, typically what happens is that the film is a disordered film, amorphous in nature. So when you form an amorphous film, what happens is that the film is of amorphous films that, as you can imagine, they don't have that order which is there in crystalline materials. So in amorphous films, the mobility of electrons becomes very small. Mobility of electrons becomes very small. And thereby, what happens is then, if mobility becomes very small, then the transistors and switches, they become slow. You can imagine, if mobility is small, the resistance becomes high. And as I've said, all switching speeds are related to RC charging or RC discharging. So if resistors become large, then the RC time constants become large and the switches all get slow. So it's an interest to make films which are crystalline in nature, which have order in them, because then the materials will have higher mobility. And so in this case, for example, the research being carried out here is, how do you print films, single crystal films, right? So you print a crystal. This is what they're describing here. So if you can print a crystal, then what you end up, you can see some of these things, you end up with getting a higher mobility material, and you could perhaps see a drain current versus drain voltage. They're making a MOSFET kind of a thing using a printed crystalline films. And as I mentioned, whenever you make something, remember there are always variations that are there. One transistor gives you a mobility of 15, another gives you of 30, some give you 5. There are always variations that are there. So that's the other challenge that one faces, that in a laboratory, you may print a film and you can take a transistor with a mobility of 35 and show a very good result. But when you actually go into the market, it's not one single transistor, but hundreds of transistors and hundreds of thousands of such products. So it's not the extreme which matters here. You will get limited by the minimum, by the worst case scenario. Or you find a way of making this distribution tighter. So tolerances and all of those things are very, very practical situations that one has to grapple with. And these are the things that become important when you go from laboratory to the market. You have to fight with these challenges here. So time is limited. Our quiz starts at 6:45. I want to wind up with showing you some of the some more challenges here. So some of you may be, hearing about these flexible displays, rollable displays and flexible displays. So I'm showing you various kinds of displays, something that can be just simply flexed a little, something that can be folded, something that can be rolled. So when you do that, you develop strain into your system. Whenever you roll something up, bend something up, you develop a strain. And strain can be shown to be related to the thickness of the film and the radius of curvature. So if you want to manage the strain and you want to roll it up like this on a pencil, then in order to manage the strain, you'll have to make the film very, very thin. Right? So you have to make a very thin layer of plastic, then only you'll be able to roll it up. So that is why if you're going to make your electronics on very, very thin films, rollable and all that, you have to make it on very, very thin sheets of plastic, and you have to do all of the electronics on that thin sheet of plastic. The trouble with plastic is, let me skip some of these things. The trouble with plastic is that plastics are very permeable to oxygen and moisture. So, you make something on plastic, and what will happen is the oxygen and moisture will get into it. And if I have an organic light emitting diode, the oxygen and moisture will get into it, react with the organic molecules, and destroy it. So you have to protect your devices. So protection of devices becomes extremely important. So you have to put some kind of barrier films, different kinds of films you have to put on top, so that you have to prevent water from getting into it. You can see the rate, the kind of protection that I need to have. 10 to the power minus 6 grams per meter square per day. That's the kind of moisture. If it gets into into my device, the device will get destroyed. So to create all those different kinds of barrier films and all that, one has to work very closely with chemists and material scientists to actually make some of these things that are there. So let me stop here. This was just to break a little bit of monotony from a little bit of abstract discussion that we've been having, and give you a flavor of some of the things that are happening currently, and in which our center is also, our institute is also active. Yeah, please go ahead. Any quick question? Anybody has any quick question? Otherwise, 6:45 already, I think. Okay, if not, Shahid, you have a question? Somebody raised a hand. Okay, if not, let's stop here, and then Friday we'll have a common tutorial. So please, whatever queries you have, you can email them in advance, so that I'll take them up, and of course you can ask questions live also. All right, so let's stop here then.
Sir, I have one question.
Yes. Yeah, go ahead.
Uh, sir, in the case of wanting to
You're not audible.
the screen, wouldn't that
Can
prevent
you
water and
can you
oxygen getting into?
what? Say again. You were not audible.
Sir, laminate our screen that we can prevent it from water and oxygen, all that reactions.
A part of your voice is fading out. When we touch the screen, part of oxygen and moisture. See, this oxygen and moisture are there all around us. So we are not talking about taking your phone and dipping it in water. These are there all around us. And even very, very trace amounts of oxygen and moisture will destroy your devices. For example, you will have this OLED, active matrix OLED phones, they'll get destroyed by oxygen and moisture. So these protective films are extremely important. The trouble is when you deposit a film, there are very, very small micro holes in them. If you examine a film, it may, with your naked eye, it may look like a very nice continuous film. But if you look at it under a microscope with high resolution microscope, you see a lot of porosity in it. These are very porous. And oxygen and water molecules, obviously being very small, they're able to get through it. So we have to find ways of preventing, these molecules from reaching my device. So that's a really, these are very, very challenging things. I would stop discussion and encourage you all to go and attempt the quiz. Please do that. I'll close it now.